Hello, good morning, good afternoon for some of you already. It's my pleasure to introduce now the presentation by Donofrio, instructor and consultant at the Snell Group. He will be sharing knowledge on the importance of monitoring electric motor starts.
Hello, and welcome to the presentation on the importance of monitoring motor starts. My name is Don Donofrio, and I'm with the Snell Group. I'd also like to thank LRVS for hosting this presentation. A little bit about my background. Went to the University of Texas, El Paso. Joined the Navy in '74, stayed 20 years, and as you can see, was in the submarine service. That image on the top right was the first ever 3-submarine surface at the North Pole on 6 May 1986. So that tells you two things. Number one, the epitome of reliability, being able to operate in and around the Arctic ice cap. And then number two, Don's getting old. So I was in the Navy and went to work for PDMA for a few years. They make an electric motor tester. Worked for Rockwell Automation when they owned Reliance Electric. And a little while with IVC, Industrial Vibration Consultants, and I've been with the Snell Group since 2001. Talk a little bit about motor starts. Motor starts are extremely stressful on a motor. That's the most stress most motors are going to be exposed to during normal operation. Starting currents, if you ever looked at an amp meter when you hit the start button on a motor, an analog amp meter, it pegs. That's not inertia, that's starting current. Starting current can approach 10 times the full load amperage rating that's on the motor nameplate. The more starts a motor experiences, the less longevity the motor is going to have. I like to say that a motor has X number of starts in its operational history, and then it fails. So monitoring motor starts. Motors are started in industrial facilities anywhere from occasionally to very frequently, depending on the application. A lot takes place when a motor starts, and we don't really pay attention to it normally, but if we do, we can identify many developing failure mechanisms. Some of them, the only way you can see it occurring is during the start cycle. Type of starting circuit also plays a big role in identifying various problems. Monitoring starts on these various circuits can identify start circuit faults, time delay settings that are set incorrectly, and you can monitor circuit balance for impedance and resistance unbalances. This topic is going to provide some basic theory and content to help you see the benefits of monitoring and analyzing motor starts. So, starting circuit faults. Here I have an inrush for a 75 horsepower motor. Notice it's up to about 350 amps on that startup. So there's my inrush. That's across the line. Now, some of the things that we can monitor these starts for is inrush value. What was that maximum current that was attained during the startup? How long did it take the transition to run? In this case, a little less than, about a little over a half a second. and that we see this profile of the start. We can trend that and identify mechanical load problems, rotor bar fault correlations. So some of the indications we get during startup, if I have rotor bar problems developing, I can see that affect the start profile. We can look for connection anomalies, starting circuit anomalies, and timing confirmations. So given the number of tests available on some of these motor test instruments, it seems like inrush, if they have the capability, is overlooked or just not regularly conducted. Maybe it's because there's no perceived benefit in doing the testing. Maybe it's not fully understood or just not a priority. And then in certain circumstances, a lot of these motors are interlocked and you can't shut one down and start it back up and monitor the starts, or you'll shut the whole process down. So I understand, but when you have the possibility of checking them, you need to check the inrush. Again, it monitors indication of the maximum start current, the transition time from actually hitting the start button to when it gets into its normal run current. We can identify correlating values that indicate rotor bar faults. We can verify the timing of the start circuit. If it has a start sequence and there's timers involved, we can verify the timing settings. And we can identify load-related faults. If we draw a higher current and it takes longer to transition to run, that's usually a good indication that something is wrong in whatever that motor is driving. It requires more torque and takes more time to get the motor up to speed. And again, we can monitor for circuit faults. So here's a start circuit profile, and this was a soft start. So you're seeing it's drawn a little over 600 amps, and then it transitions to run from about 1 second up to about 4.25 seconds. So 3.25 seconds transition to the run. And then at just above 15 seconds, you can see that little peak there. That's where the starting circuit times out and it goes across the line. And then at the end where it transitions to its normal run current, we can monitor for that normal current. So a lot we can do just from that starting profile, and that's not all we can do. So here's a little truth table, and if we monitor the current peak trend and the transition to runtime, I can look at those and I can tell whether I have a high resistance connection, a mechanical load problem, or a rotor fault, as well as other problems, and we're going to discuss them. Let's do a little motor theory review, nothing real heavy, but just so we can understand how the starting circuit's affected. So first off, we're going to talk about the polarity of a magnetic field. So we have this thing called the left-hand rule for coils. If I grasp a coil in the direction of the current flow in the coil at that instant in time, I wrap my fingers in the direction, my thumb is always going to point to the North Pole. So if I apply AC to that coil, you can see here on the positive alternation, the south is on top and the north is on bottom. When we go to the crossover point, there's no current flow in the coil. I have no magnetic polarity. And then when I hit my negative peak, the north is on the top and the south is on the bottom. So every alternation, the polarity in the coil changes. When I apply an AC signal to the motor windings, which are essentially coils, I'm going to have an overall north to south pole arrangement as that rotating magnetic field circulates through the stator. Here you can see this is a representation of a two-pole motor. I have an A pole and an A prime pole at 6 o'clock. I have a C prime and a C, and a B prime and a B. So I have one pole in each half of the rotation of the motor, two-pole motor. These are wound to give us an overall north to south, and they're physically 120 electrical degrees apart. So when we apply a three-phase sinusoid, which is represented here with a brown, orange, yellow, 120 degree phase separation, this is what it's going to look like, the signal that's applied to the stator. Now, the rotating magnetic field in the stator, we're going to step it through a sequence in 60 degrees. So here it goes. Now, note at each 60 degree step, there's one phase that has no current flow in it. So it doesn't jump from phase to phase to phase, it transitions. between phases. Right now, we see the overall north to south magnetic field is from 9 o'clock to 3 o'clock, and there's no current flow in A. When it steps again, there will be no current flow in C. And steps again, there will be no current flow in B. So this rotating magnetic field in the stator is going to cut through the rotor. And the rotor has bars that runs the length from one end ring to the other, and then on the opposite side, we have rings continuing on. So the current's going to flow from the rings to the bar, through the bars to the end rings, and then down the end ring to the opposite side of the rotor and flow in the opposite direction. That's going to create electromagnetic field around those rotor bars. So we're going to have an overall north to south magnetic field on the top and the bottom of the rotor at any instant in time, and that's going to try and lock into the rotating magnetic field in the stator. Current flowing through the rotor bars creates that magnetic field, and that's what tries to lock in north to south with the rotating magnetic field in the stator. So the speed of that rotating magnetic field can easily be calculated. In this formula there, you see NS, that represents the synchronous speed of the motor, is equal to 120 times the applied frequency of the AC signal. So in the United States, we use 60 hertz. So 120 times 60 is 7,200 divided by the number of poles. We were using a 2-pole motor. So 7,200 divided by 2 is 3,600. That's how fast that synchronous RPM is going of that magnetic field in the stator. Now, slip, that's the difference between the synchronous speed of the rotating magnetic field in the stator and the RPM of the rotor. And we can calculate that very easily. We take the synchronous speed minus the RPM of the rotor times 100 and divide it by the synchronous speed. So the greater the difference in speed, the more current is going to be induced into the rotor. That's just some basic AC generator theory. We're also going to draw more current, and we're also going to produce more torque with greater slip. So what's the slip when a motor is started? When we hit that start push button, the rotor is at 0 RPM. So I have 100% slip at that instant of starting the motor, which means I'm going to have a maximum amount of current, and I'm going to have a high amount of torque. So that generates what we call starting current and torque, or locked rotor current and torque. Here's a starting current and torque curve, and this is going to vary by motor design, but as you can see on the left vertical axis, we have the percent of full load torque and current, and on the bottom, we have the percent of synchronous speed of the rotor. So when we hit that start push button, we're drawing 625% of the full load current, and we're producing about 215% of the full load torque. So as the rotor starts increasing speed, the current starts dropping, the torque drops off for a little bit and then pulls up. And at 100%, the torque and the current are right on top of one another, and that is where we're producing 100% of the full load torque, and we're drawing 100% of the full load current. That's where the motor is most efficient. Now, whenever I'm initiating a start, we have a huge amount of current flow in the stator, and we induce a huge amount of current flow into the rotor. And if we don't pay attention and we have a locked rotor situation and circuit protection doesn't trip, we can burn that rotor up and the stator. Another problem is if you initiate too many starts without providing adequate cooling time between the starts, you can actually cause damage to the stator and the rotor as well. And I've encountered this many times over the last 20, 30 years. Oh, analyzing inrush. So here we have a inrush cross the line start. And then here we have another inrush, but we have one superimposed over the baseline. So the baseline's in the blue, and the one superimposed is the same motor during the startup with broken rotor bars. We have less current because of the broken rotor bars. The rotor bars are like resistance in parallel. I have less resistance in parallel. I increase the equivalent resistance or impedance of the rotor. I have less current on startup. But because I have less rotor bars, I have less torque. It takes longer to transition to run. And you can also detect a little bit of a ripple there caused by that broken rotor bars on the rotor. You have an area where there's no current flow, there's no magnetic field interaction, and it causes distortions in the current. We can actually see that in the inrush. Now, different types of starting circuits you have across the line is seen on top here, and then we have, used to be very common, but VFDs have replaced a lot of these, a solid state reduced voltage start, or otherwise referred to as a soft start. You have a logic controller that gates SCRs. The SCRs are going to drop voltage and reduce current going to the motor during the time sequence of the startup. After the time sequence, it times out and goes across the line. So here we can see both across the line start, and here we can see a 400 horsepower motor. Notice it's only drawn about 850 amps. It could be drawn 4,000 amps on startup. So that soft start mitigates a lot of that starting current. And you can see just under 10 seconds where the soft start times out and it transitions to run. Now here's a soft start where the timer went south on it, and it's only timing out at about 3 seconds when in fact it should be up here around 8 to 10 seconds. Here's a case study where we have a impedance imbalance in the rotor. The rotor itself is causing 10 to 12% inductance unbalance. Position of the rotor in relation to the stator when you're measuring inductance has that unbalance, and it affects the startup. You can see there with the circled current on the slide there, we have 526 amps in phase 1, 397 in 2, and 402 in phase 3. That is because of the varying impedance of the rotor. We can trend that. If I have a normal rotor and I start trending unbalanced on startup, I could have a rotor problem developing. Here's a couple low voltage start configurations, series reactance, series resistance. You basically just put a coil or a resistor in series with the motor windings during startup. You're going to drop voltage, you're going to reduce the current, and it's going to take longer to transition to normal run speed. VFD, I'm just showing a box there because all the different circuit configurations, but you're going to vary the voltage and the current going out to the motor to maintain whatever desired RPM. Then we have a circuit that's used on a lot of medium high voltage motors to mitigate starting current. This is an auto transformer reduced voltage start. It has what they refer to as a start reactor, which is just simply a series of windings, and we can tap at different levels. You can have the whole winding in the circuit, or 80%, 65, and 50% are some normal tap arrangements. So again, we're going to drop voltage across that start reactor, reduce the current to the motor during start. Here's a VFD on startup. Vary the voltage, vary the frequency to maintain whatever RPM or attain whatever RPM. And here's a start reactor. This is a 4160 volt motor. And right there at about 15.25 seconds, you can see where the start reactor times out and it went across the line. Now here's one where we had a problem with a start reactor. You can see the start circuit schematic there on the right and the bottom. And what happened was they had just installed some new variable frequency drives in one area of the plant. And whenever this particular motor was started, it would trip those variable frequency drives off the line. When we tested the starting circuit, we immediately saw that what was happening was the phases were not equally tapped. So if you notice the current up there on the top, we're drawing 1,334 amps in phase 1, 984 in 2, and 851 in phase 3. That huge current draw was causing a voltage, more of a voltage sag on phase 1 voltage, and that unbalance was causing these VFDs to trip off the line. The start circuit was properly tapped and everything worked fine after that. Here we have a normal variable frequency drive on startup. You can see the current and the voltage. And the current is starting low and going high, and the voltage is staying fairly consistent across the startup profile. Now here's the phasor diagram and the time domain for the current that VFD is producing. Everything looks pretty balanced, and phasor diagram looks 120 degrees between voltage and current, and equal magnitudes of each value. Now that motor failed, and when they got the motor returned from the motor shop, we tested it to make sure everything was fine. And what we determined was the VFD had a serious problem. Look at the difference between current 1214, 1276, 957. Voltage is pretty balanced. But we look at it a little bit further. Look at the phasor diagram. We're missing almost half of the phase 3 current. And we're missing some of the phase 2 current. And look at the time domain over on the right. You could see where the phase 3, which is in red, has been clipped, and also the phase 2 in blue. So this was causing an immense amount of heat in that motor, and it caused the insulation probably to break down and fail. So here's a Y start delta run. Here's a partial winding start motor. This is a configuration that's used on a lot of applications in the lumber industry, and basically use part of the windings to just start saturating the core and the rotor and the stator, and then after a couple seconds, it starts all the windings and the motor starts. Again, it's very rare except in. All right, so here's a case study. This is a 50 horsepower 2-speed fan. Normally, it's going to start and slow and shift to fast, and we can see the change in current at about 24, 25 seconds. Okay, that's normal. Well, here's another one that was starting in fast and shifting to slow. And the timing circuit was taking like 14 seconds for it to actually start after you hit the start button. Now here's another one that started in slow, but when the fast contactor closed, it was shattering. It wouldn't lock in. The contactor was bad. So the contactor was replaced, and the motor operated normally. So trending the peak current and the transition to runtime. If those values remain the same, then basically everything's normal. But if it's lower in one channel and it takes longer to transition to run, so I have lower current in one channel, that means I've got a high resistance connection problem somewhere in that start circuit. Higher in all channels and it takes longer to transition to run, I have a mechanical load problem. Something in that load is requiring a lot more torque to get the motor moving and get it up to run speed, and it's going to take longer because of that increased torque requirement. It's going to draw higher current, and transition to runtime is going to take longer. Now, with broker rotor bars, as we mentioned, we're going to have greater rotor impedance, so my start current is going to be lower, and it's going to take longer to transition to run because I have less torque with those broken rotor bars. You may also have ripple in the current, like I showed you in that one PI or starting circuit profile. All right, and that's it for this short presentation on the importance of monitoring motor starts. I want to thank you for sitting through this presentation, and if you have any questions on anything that we covered, and believe me, there's a lot more involved in this and what we just touched on. Send me an email at ddonofrio@thesnellgroup.com, or you can go to our website, and there's areas there where you can submit questions at www.thesnellgroup.com. Again, thank you for sitting in on this presentation.
Any comments, questions? I'm not sure if anybody else has joined. I don't see any questions on the chat. We'll give it a couple of minutes and then we will adjourn.